have got this function select codes, and those function select codes, as I mentioned before, there are two inputs in our previous data path, G and H, and they require 4 bits for G and 2 bits for H. But there is a simple transformation between function select and G select and H select, and this transformation is summarized in this table. As you can see, there is an MF, mux select input. When it is 0, that means you're basically selecting the arithmetic logic unit, ALU. That's why we got all these bits here, and don't cares for the H. And for the MF equals 1, we have shifter operating and the ALU disabled. So that's why we got those don't cares for the G input and 0, 0, 0, 1, and 1, 0 for H to be able to select the right operations. You know, copy operation, right shift by 1 bit, and left shift by 1 bit. Okay? And this is the control word that results, because control inputs are essential for data path to operate accurately. To be able to execute an instruction, we apply these control values for each clock cycle. So it's a single clock cycle, as I mentioned before, where you have got to finish every single one of those operations inside a period, a single period here. And in that period, while you're executing these instructions, add operation, simple XOR operation, other logic operations, you have to also generate through a control circuit these control bits, 16 of them, and you have to supply those 16 bits to the data path so the data path can execute the corresponding operation. The names of these fields are DA for destination address, 3 bits in this case. If you look back on our previous data paths example, we used n bits to address these registers in the register file, but now I set n equals to 3 in my example to show you how the control word looks like. You can see that DA is 3 bits, AA, which is the source address A, or one of the operands actually, is 3 bits as well, is another address, and BA is another address, okay? MB is one of those, MB and MD are one of those muxes that enables us which input to select. If you look at our illustration, you can see that this mux, MB select, helps us select either constant in or one of the outputs of the register file, or function unit. If you look at the function unit, you have this mux selecting either the output of the function unit or something from the memory that we call it data in. Okay? In order to load something to the register file, you have to take something from a memory so that you can operate on those values. Okay? In the beginning, those registers are empty, remember, and they need to be filled from outside, and usually that outside entity is the memory, okay, main memory. All right, so let's just go through these examples. As you can see in this example, I've got 7 different instructions, and you worried about them? Okay, I'm not gonna step on him. Okay, I promise. So you got these 7 instructions. We got subtraction, left shift, 2 additions, and they're continuously. And this is very important because this enables us to transfer something to the memory. Okay, and this is from memory to one of those registers. So these are like reading and writing from the memory, reading something to memory, and zeroing out. This is also very crucial because before you start doing some operation, you have to zero out one of the registers, right? You want them to store some zeros so that you can operate on that. So that's why one of the important instructions is just the zeroing them out. Okay, you can see here, in order to do subtraction, I use R2, R3, and R1. R1 is my destination, okay? And R2 is one of my operands, and R3 is another operand. And I would like to execute this subtraction operation. And as you can see, in order to do the subtraction, I have to select MB to be 0, because I'm not getting any constant from outside, okay? Remember, MB was constant. And function select has to be 0, 1, 0, 1. If you don't need to memorize that, you just have to go back to this table and search for the subtraction operation. Which one is the subtract operation? Of course, this one. Because this is A plus B, which is 1's complement of B, okay, which is B naught, plus 1. That is your subtraction, and that corresponds to an FS select of 0, 1, 0, 1. Okay? That's why you have to select 0, 1, and 0, 1 here. And MD select is 0 because you're not getting something or writing something outside. Remember the MD? You don't need to memorize anything, by the way. Okay, MD is right here. You're not reading or writing anything to outside, so that's why you have to select MD to be 0, so that puts something on this bus. And finally, we have writes, because we need to write something to R1. That's my destination. That's why I have RW read write set to 1, so that I can write something. Okay, so you see the control word is constructed by just looking at the instruction. There's a one-to-one map. Once the meet operation given to you, or instruction given to you, you can generate the control word by using the tables. Okay? So you can see here, our control word is 001, 010, 0110, 01010, and 1. Okay? Similarly, you can do the same thing for left shift. In the left shift, there are 2 registers. One is the destination, you can see, and the other is the second operand, which is we call it B, but not the A. That's why A is just empty. That's don't care. Okay? This is, again, you have to look at the data path in order to understand this. Our hardware does not allow us to use this operand for shifting purposes. The shifting happens only with the BA. Okay? How did I understand that? By just looking at the corresponding data paths, of course. Look at this data path. In order to shift something, you see, this is your output. This can be either constant or this, but this is your B select, not A select. So if you take an input from A, that A cannot be shifted because it's not connected to the shifter. Okay? That's why we have got don't care here. Okay? So this is don't care. This is R6, as the instruction says. So I put 110. MD is 0 because there's nothing constant here. Left shift turns out to be 1110 from the table. Function is 0 because we're not writing, or the MD is 0. Sorry, not functions. MD is 0. That is, we're not writing, reading the memory. Okay, and we write the result to the destination output. Okay, so separately, the control word here is 100. You can choose this, then anything you like. There is no such a thing as don't care in the hardware. You have to select that something, 0 or 1. So you select 0 or 1 here, and then 110, 0, 1110, 0, and 1. Similarly, this is an incrementation. You can actually implement those instructions in different ways. There is no unique way, by the way. For example, this is already supported in the function units. But you can also use treat this one as a constant, and use another instruction. Okay? So for this, for example, I use the incrementation facility of the function unit, because the function unit has this operation, A plus 1 equals F. So I use that. So this is R7 again, and this is don't care. Okay? Because we don't use that by B, as you can see. 0 is 0 because we're not really getting any constant. Okay? This is the function unit that helps us implement incrementation. This is 0 because we're not getting anything from the memory or writing something from the memory, and we write the destination. Okay? And as I said before, it's not unique. You can actually set MD to 1 and push that 1 as a constant, okay, as part of your instruction. And that would also do it. Okay, so here is the R0 plus 2. So that's another example that you should, you should be able to implement it using a constant, because it's not 1 anymore, it's plus 2, and there is no such a plus 2 type of operation in the function unit, so you treat this 2 as a constant. This is your R1, destination, R0 is one of the operands, the other operand is don't care, and we got 1 and B, 1, because now we're getting 2 as a constant from outside, and we have to add operation, and our add operation is 0010, and MD is 0 because we're not writing or reading to the memory, and we're writing to the destination. Okay? Now these two are very important because these are allowing us to read or write something from the memory or to memory. You see that these two the operands are all don't cares. Okay? The only thing that cares, that we care, is R3, that is the register that contains the memory address. Okay? That memory address is on B because again, this is based on our data path. Data path, data in, data out, only connected to the source B, not source A. That's why we have this R3 selected 011. Whatever that R3 contains is our address. So we have to use it as an address. There is no constant, nothing about constants happening. Functions also don't care because we're not doing anything, doing any mathematical operation. So it turns out we don't care. MD is don't care because we actually are communicating with memory, not the, we're not reading something from the memory, we're trying to write something to memory, okay? So if you look at the data pad carefully, you see, if you're reading memory from memory, then MD select is important. But if you're writing something to memory, you see these two buses? One of them is address, the other is the data, okay? So that's why I said B is our important, source B is important for us because that's what we care about the data, okay? So that's why this function unit is not operational at all when you're writing something to the memory. Because up to this point, you're done. You already sent the address, you sent the data, so it's written, okay? Of course, the memory has to be enabled. That's another control signal that's not part of the data path, okay? Okay, so here, you got this. The read operation is different because now you have to have MD to be 1 because you're reading something from the memory. That's why MD is now 1. And you're writing some to destination. That write is also 1. But the rest of them are all don't cares. You can see that. Okay? Except R4 because R4 is where you're writing the data. Okay? That's your destination. And finally, zeroing out. Well, I use the trick here because if you XOR two numbers bit by bit, what you get is 0. I use that trick to zero out the register content, and I did this R0. I selected R0. You can select any register here, by the way. I selected R0. I selected R0 and R0. Put them through an XOR gate. Okay? If you put them into XOR gate, that's going to do an XOR operation bit by bit, and the result is all zeros. That 0 is written to R5 because I'd like to zero out R5. Okay? MB 0, MB is 0 because you've got nothing to do with the constants, nothing to do with the memory. And you finally write it to destination. Okay? One bit. Okay. Last time I started talking about, before that, we have quiz question, right? It's a quiz question. Okay, so let me go through the quiz question really quick. Okay. All right. So, the quiz question was asking two instructions and their control word, namely R7 gets the data from R3, but that R3 is multiplied by 2. We know that this is not supported by our instruction set, right? There is no multiplication, such that if you look at the function unit, the table for the function unit, right? So let me just go through this FS codes real quick. You see, there is no such instruction defined in our function select codes, all right? So therefore, I have to do something here. So instead of implementing this, maybe, and this is one option, by the way. It's not the unique option, but you can just do R3 plus R3, right? That's one option, okay? You could have done shift, for example, because multiplication by 2 is a left shift by 1 bit, okay? So you could do that as well, okay? But I'll just do this because I think in my opinion it's easier because we've done this multiple times. So this is R3 plus R3, and the answer, the result is written to R7. So the control world, we have to determine 3 bits for the destination. Destination is 7, and I know that the 7 is 111. Okay, that's just address, right? So I put the address here. The first source is AA, okay, which is R3, right? A and B are the same, by the way, in this example. So R3 is 011, right? Yeah. And BA, or source B, is also 011 because it's R3 too. 3 is the address, right? So I'm just coding them, coding these decimal numbers in binary domain. These are going to be my addresses, okay? And the next is MB. Okay, in order to remember what MB was, I don't even memorize myself. So I urge you to look at the data path, okay, to be able to figure out what's happening. MB is the mux that determines whether a constant n is going into the system or something that you're getting from the register file. In this case, we're getting this from the register file, right? Because it's R3, right? That's B, that's A. So therefore, I have to choose one bit, 0, so that the corresponding input-output relationship is satisfied. Okay? Next is FS, which is 4 bits, as you know. So I look at the table again. All right? So you don't need to memorize anything, you see. I'm looking for what? The plus sign, addition, right? So I look at the addition, I figured it out. A plus B is here, so which corresponds to 0, 0, 1, 0, function select equals 0, 0, 1, 0. That's my function select. There are 2 more bits. One is for MD and one for RW. I'll just read right for the register file. If I look at MD again, I'm going back to, this is the procedure, that's why I'm actually walking through step by step. That's the procedure you should follow, to figure out the control word. I look at MD. MD is the mux that determines whether it's something I'm reading from the memory or something that is coming in from the function unit. Okay? And in this case, the function unit is operational, which sends that information to mux D. So therefore, I have to select 0. Okay? So that I can get the output of the function unit and put it on this bus. Right? This bus, right here. Okay, finally, do I write something to the register file? Yes, I do. And in fact, the 7th register is written. Okay, what is it written? The written value is the value that is calculated based on the contents of the R3. Okay, actually multiple times in this case. Okay, so this is written back to the register file, the corresponding register R7, so I have to enable it. So I put 1 to enable write. So you enable write here, and then you send the address to the register file, so the register file can write exactly in that location. 111. Okay, that's your destination address, right? And this one. Destination address. If you would like to be a bit more detailed, you can go back to what's inside that data path. That's your destination select, right? In this case, there are 4 registers. In our example, we have got 8. That's why we use 3 bits to address them. Okay? So this example is not directly applicable, but we're talking about some extended version of this data path where you have 8 registers instead of 4. Okay? Got me? No problem? You got a question?
When would we use MB?
What?
When would we use MB?
MB?
For constants, right?
Yes, right?
So anything like, I don't know, R3 plus...
Yeah, R3 plus 3, for example.
Then we would...
R7. You can directly use constant, because this is coming, as you will see, this will come from the instruction. We will read that value from the instruction, and then put it on that bus here, constant, right here. So you can now select a 1 to put that into bus B. Okay? You have got a question?
What if the read and write is 0? What will happen?
You usually have a 1 here, because you usually write something to register file. But sometimes you don't have to. For instance, if you would like to write something to the memory, then you use these 2 buses, right? You've got nothing to do with the rest of the circuit, nothing to do with the register file. You read something from the register and you write it to the memory. So you don't need to write anything to the register file. In that case, you have to disable it. Why? If you don't disable it, wouldn't that work? It may work, but you basically secure yourself for data corruption. Okay? I mean, things can happen. There are a lot of errors happening inside this circuit. If you disable this for writes, then you can protect your data.
Is it the load enable?
Yes, that's the load enable, correct. If you set that load enable to 0, those AND gates will generate 0, 0, 0, 0. That means those are disabled. You cannot write them. But if you set that load enable to 1, which is your read-write, that's going to make those AND gates pass whatever the other input is, right? So that will pass this to the, and so register file could be enabled. These can be enabled. Okay? Any questions? Any more questions? Okay, so that was our first question. The other question was data out and R7, right? And this was actually part of our examples, right? So if you look at the examples, we already have a use case, which is right here. So what does that correspond to in physical terms? This actually corresponds to this example. This means the contents of R3 is written to some address in the memory. Okay? So therefore, the destination address is not applicable. So that's why we have that don't cares. The source A is not applicable because we're dealing with source B. So that is also don't cares. You could have just put zeros and ones here, but it wouldn't matter. Okay? The result wouldn't change. And R3 matters because if you look at the data path carefully, let's just look at the data path again. You see the data path? If you would like to write the data, then you have to use bus B. And that is connected to either the constant or B data. So therefore, this address is important because that's where your data lives. Okay? If you'd like to write something to the memory, you need two things. One, address of the memory, where you want to write, and the data itself. And data is on this bus B, which could be coming from here or here. So if you select MB to 0, then you can send the data from the register file. And in this case, we're doing that, exactly that. We're sending the data that is contained in R7, okay, to the memory. Okay? So therefore, the first A, whatever the address is, okay, is going to tell us where we are writing in the memory. Okay? So usually, if you look at this example, you see this example, this is the address actually. So I put it don't care because there's nothing to do with the data. Okay? But in general, in practice, you probably have an address here telling us, the address is of course not 3 bits. 3 bits, this is the register address. But that register contains some data, right? That data is not user data. That is memory address. Somebody has written that register sometime in the past. So you can use that address. Okay? And the data that is stored in R3, but in our case is of course is R7. So let me just fill this up for you to be able to precise. So my DA is just don't care because I'm not writing to the register file. This is my address actually, but you can't really get that address from this description. Okay? This description is about data, not the address. That's why we have don't cares here. But this matters because this is where the data lives, and the question says that the data lives in R7, so you have to put 1111 here. Okay, so that I can read the data from R7. Okay? And next is MB. Well, in this case, MB, as you can see, is 0 because you're reading the data from the register file, not the constant, right? That's why this is 0 still. OFS, that is X because we don't do any computational manipulation, right? So that doesn't really matter, as you can see from the same example. Okay? And MD is, as you can see, also don't care because MD is concerned after the function unit, right? But we've got nothing to do with the function unit when we write something to the memory, according to this data path, right? You see the data path? Once you send the address and the data out, you're done, basically. Because from that point on, it's about the functional operations and selection from if you're reading from the memory or from the function unit and writing something in register file. These are not something you're concerned with when this instruction appears in your code. Okay? Because this is a write operation to the memory. That's why we got this don't care and finally read write. This is also 0, right? Because we don't want to write anything to the register file. We would like to protect our data. Okay? Okay, good. Any questions?
Can I ask?
Yes?
Is it possible to write don't cares in BA and write one ones in AA?
Is it possible to write don't cares to BA?
Yes.
No, it's
Why?
not. Because don't care here, if you put don't care, that means you're not answering this question. This question says that R7 has the data.
But we can put ones in AA.
1, 1, 1?
Yes.
You cannot do that because you see, this is your data out. You see data out? Data out, which means that this bus carries data. This bus, on the other hand, carries the address. Since your B is connected to bus B, which carries the data, then you have to put 111 in the source B address, not source A address. Okay? This is just definition, you know. If you just switch these two, for example, these are going to the memory, right? The memory has an address input and a data input. This data input is connected to this, and the address input of the memory is connected. So let me draw it here. Maybe that can make it more sense. So this is your memory, this is your address, and this is your data, right? And there's an enable, of course. I'm just saying that this data out is connected to data input of the memory, and address is connected to the address of the memory. Okay? That's why we have got 111 in source B address. But if you just switch them, in other words, if you connect address out to data and data out to the address, then what you said would be true.
When we receive address out,
I just used it. Without using address, you cannot write data, right? I just assume that this is a don't care. But in practice, as I said before, this is not a don't care. This is some register has an address value that you would like to write to. Okay? Here I just said don't care because any address value is okay for me. But in general, operating systems fill those registers with appropriate addresses so that you can use those addresses because other address places are already filled with other data. You cannot overwrite them. Otherwise, you lose data. Okay? Is that clear?
Yes.
In this case, you know, for the practical purposes of solving this question, I just assume that any register is okay. I can just use any register because those registers contain either 0 or some random number. But it's okay for me because I assume memory to be all 0, all empty. Okay, all empty.
okay.
Okay? All right. Okay, so let's just continue real quickly. Got a bunch of more stuff to discover today. Okay, so here is so we learned about control pad, we learned about data pad. So now when we combine them, let's just combine them to make up the conventional computer design or computer architecture. And as you can see, this is how the things are placed in an architecture, the typical architecture. And you can see the control unit consists of instruction decoder, a program counter, which we will explore in detail. And this is your instruction memory, usually in the form of ROM, read-only memory or random access memory, RAM. Okay? And this is your data pads, and this is your data memory. This is the data memory I was talking about. Okay? So now you can see that those are all arrows. So let me just go through the arrows. So the control unit generates the control words. Control words are right here. The control word that we came up with, right? Those are the control words, and those control words are the output of the instruction decoder. Okay, we'll come to this. Because instructions are actually shorter sequences. You can see there are IUs, how many bits here? 16. I will add more to that. Because, for example, the data memory enable is not in this control word, right? I mean, MW, right? Memory writes. It's not part of the control unit, the control word yet, but we will add it. And also, I talked about branch and jump type of instructions in our last meeting. If you remember, if you encode a for loop or a while loop, you have to go back to where you left. So in order to do this, you have to have a certain instruction that will enable you to move, in a linear fashion. I just assume that instructions are handled one after another, right? But if you would like to go back, then there has to be an instruction to do that. And those instructions are usually referred as an umbrella term of branch or jumps. Okay? So if you add them as well, that will also add some bits to the control word. So control word can be any length you want, but the instructions are not. Instructions are actually your architecture's essential parameter. So for instance, you may have heard it. My architecture is 16 bits. My architecture is 32 bits. Now probably your architectures in your CPUs are 64 bit, for example. 64-bit AMD, 64-bit Intel CPU. Okay, you may have heard this before. This is the instruction length actually. This the register lengths and instruction lengths. This is how the architecture's bit count is determined. Okay, so therefore your instruction memory will have, for instance, in this example, 16-bit long instructions. They will go to the instruction decoder. Instruction decoder will generate the control word of any length you want. In this case, it's 16-bit right now, but we will increase the number of bits here in the control word, and that will feed the data path. It will tell the data path what to do. Of course, the data path will have some feedback to change, for example, something in the construction decoder or change something in the program counter. What's program counter? The program counter is like a pointer. It tells you where you are in your instruction memory. You see? It's just a counter. I talked about this in our last meeting, as I remember, right? So it's like, unless there is a branch or jump, it will actually increment one by one. Okay? So your instructions will be executed one after another, one after another, one after. Your compute machine is this control unit and data path. Okay, sometimes you've got some relationship with the data memory because your registers are incapable of storing the data because data is huge. That's why it has to be in communication with the data memory. Okay?